Hello, 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 hello. Hi. It is Tuesday. I don't normally record on Tuesdays for some reason. I don't know why, but by happenstance, I don't typically do. But you know what? It's probably because I'm tired. Despite Tuesdays being the best days of the week, I guess I did record that one on a Tuesday, but I think that's the only other one I have. I typically don't. And so today, I wanted to get more back into the technical aspect of these pep talks, like teaching you and hopefully entertaining you with concepts that you probably experience it every day, and this one you definitely do, but that you might not know practical things about. So today, as I round the same corner I always do when I announce it, today we will be talking about fluids and what they are. Now, you can't study aerospace engineering without having an understanding of how fluids work. It's just impossible. And even though I was space track, and even though my specialty and my concentration was human factors and life support, I still know how fluids work. It is a straight-up requirement for everything, and I know how they work in the body, too. So that comes in handy sometimes. But I want to talk about the main guiding principles for fluids and how they compare to other states of matter, as well as very practical things that affect your everyday life, like cooking, or running, or swimming, or driving your car. There's a couple of them. But, so yeah, let's get started. So fluid. Fluid. What is a fluid? Well, a fluid is a state of matter, matter that is in a state that is not solid. Now there's like 5 states of matter. You know solid, liquid, gas. There's also plasma, which is superheated above the gaseous state. And there's the more experimental Bose-Einstein condensate, which is frozen below the solid state. And you get so cold that like electrons start doing weird things and not orbiting in orbitals anymore, and they start getting closer and closer to the atomic nucleus because it's weird. Those Einstein condensates are rare. You probably won't run into those at all in your life, but you will run into gases. You will run into liquids, and maybe if you have a lava lamp, you'll run into a plasma. Although the plasma there is not necessarily true plasma. And also, stuff like blood plasma isn't necessarily true plasma either, but we use the same word for it. But yeah, so hopefully this will be a enjoyable, entertaining topic, and very practical. So, fluids. Non-solids. It means they can change shape. That's the main defining characteristic. And you're currently living in a fluid. You're hearing me through a fluid. Sound travels through air, which is a fluid. And I'm not just talking about gases. I'm also going to talk about liquids, because the properties and characteristics that you ascribe to one, you can also ascribe to the other. The principles all pretty much work the same, although you have the difference between liquids and gases is that gases are typically compressible and liquids are incompressible. That is the underlying characteristic between them that separates them. What that means is you can squish gas, you can't squish liquid. And if you can put it under pressure and it will deform a bit, but not to the same levels that gases will under pressure. Gases compress. And anyway, there's this also an interesting property. You learned this stuff in middle and high school, but there's a relationship between all fluids, between temperature, pressure, and the volume that they take up. And there's some more. You can derive things off of that, as well as like molecular counts or molar counts, which is more talking about volume and how much stuff there is in a set volume. Although that's directly dealing with density. But density is just the inverse of volume. You can talk about velocity. There's really cool velocity effects with fluids, which I will get into because of my aerospace degree. We study fluids when they're not moving so that we know how they work when they are moving, or when things are moving through them. Let's see, what else? Fluids also have a property that is more unique to them compared to other states of matter, known as viscosity. It is how freely a fluid is able to move or flow. It's a measure of its liquidity or its ability to change shape. It's a property of the matter itself, which is pretty darn cool. So stuff like gas has a very... When I say high or low, I'm going to use terms of more viscous or less viscous. That's the proper adjectives, because I don't want to put numbers to it. You probably aren't familiar with what I would mean with the numbers. But the units are usually measured. It's weird. It's like kilograms per meter, or kilogram meters per second. Wait. See, I know it's different for SI than it is in standard, because one it's like pound or slugs per, or pound mass or something per foot per second squared or something. Basically, it's flow rate. It's how much matter flows through this distance over this much time is the conceptual characteristic of it. So things that are highly viscous, low viscosity versus high viscosity. I always get this mixed up, but things that have high viscosity flow faster than things with low viscosity, I believe. I think. I'm pretty sure. Or it might be flipped. I always get it mixed up. But the more or less, if it's flipped, viscous your fluid is, the harder it is for it to flow. So like maple syrup is on one end of the viscosity scale, while water is on another. Like maple syrup flows very slowly. I believe it has high viscosity. I'm gonna go with that. It flows slow. Water flows pretty average. And then there's supercritical fluids and other fluids that have much higher viscosities because their temperatures are adjusted. So things that are hotter tend to move faster because temperature is an average measure of kinetic energy, but also their molecules are more loose, and thus they don't hold their shape as well. So things that are nearing their critical point or supercritical point, which is the temperature and pressure and volume at which a liquid turns into a gas, has a different viscosity than if it's near its freezing point. Now this matters for a few things. If you're swimming, for example, the reason that you're generating force while you're swimming is because fluids have a viscosity to them. You're able to push off the fluid instead of just moving it around because it's trying to hold its shape, and you're moving faster. Well, ideally, you're moving the liquid faster than it changes shape, and thus that creates resistance, and thus creates a force. I'm in the opposite direction. Like, imagine like paddling your hands through air to try and move. You can try that, but you probably won't move or get very far. You can. That's how fans work. But if you're paddling your hands, it's because air is it's able to flow very easily, and you don't get much resistance or much force. There's also not much air there, comparatively, density-wise. There was a study done, I saw a YouTube video on it recently. Well, there was a study done on this years ago of basically swimming in maple syrup versus swimming in water. And you'd think you would go so much slower because maple syrup is thicker and it flows slowly, it's hard to get through. But for the same amount of time, as long as you have energy to spend, it is easier to swim through maple syrup than it is water because you're able to generate more force off of it because its viscosity is higher or lower. See, this is really bothering me that I don't exactly remember which is which. highly viscous, low viscosity. Ah, man, it's gonna bother me. I'll have to look it up when I get home. Anyway, the viscosity is something cool that you don't find with solids, that you do find with, well, I guess they technically have zero viscosity. That's what makes them a solid. They're not able to flow, typically. Another thing about fluids, there's some cool principles. I talked about how they're all related to each other in different ways, and you've probably seen the ideal gas law, PV equals nRT, PIV nerd. P is pressure, V is volume, N is the number of moles, N is the number of moles, R is the a universal constant, but it's in units with moles, and then T is temperature. There's also another version of that equation that takes moles out of it, because we don't unless you're a chemist, you don't typically deal with moles. And that one is P equals rho RT, I believe, or PV equals rho RT. In this case, rho, no, there wouldn't be a V there, because rho covers that. Rho is density. The symbol for it looks like a lowercase p, but it's a Greek symbol. P equals rho RT. And in that case, the R pulls in a certain value affixed to it, the amount of mass you have, not your molar count. And the P is 1 over volume. It's density. So that's another more practical principle. But you can relate things to each other using this principle. And there's cool effects you can do with comparing one fluid to another using it. So an interesting thing, and I'm driving right now, as you can hear, is the Bernoulli's principle put in effect. Bernoulli was, he's an old physics dude, old physicist, but he had this principle that related velocity with fluids, pressure, and volume, and the ideal gas law. And a little bit of temperature, but it's not necessarily temperature dependent. Well, okay, they're all dependent on each other, but the point is it has the least of the effects. And so Bernoulli's principle simply states that the faster something is traveling, like the faster a fluid is traveling, the less pressure it has, which is interesting. You think that's kind of like the opposite of what you think. And also, this only works up until you hit the speed of sound for your fluid, and I'll talk about that in a bit. But Bernoulli's principle is interesting. So you've definitely had this before. If you're sitting at a stoplight, let's say you're in a turn lane, you're sitting at a stoplight, and you're on a 2 or 3 lane highway, and cars are just whizzing past you, right, on your right. And every time a car whizzes past you, your car jerks a little bit and heads, kind of dips in towards the lanes of traffic whizzing past you. And then you'll get a tractor trailer or something going past you at 65, 70 miles an hour, and your car just immediately yanks itself sideways towards where the tractor trailer is. That is the Bernoulli's principle in effect. So what's happening there is the tractor trailer is moving fast, and there's air that is moving with it and around it at speed, and the trailer itself is accelerating air as it picks it up and drops it off by way of friction. And what's happening is there's an airflow between you two, and because you are stationary and it is moving, there is a difference in the airflow. And what that happens is because the air is flowing and there's a relative difference, it creates a low pressure zone between you and the tractor trailer. And that low pressure zone causes, it's a not a vacuum, a pure vacuum, but it causes a minor vacuum to form. And it rushes in just basically the gas that's around your car towards that minor vacuum to fill it, because nature abhors a vacuum, as you've probably heard before. And so what you're feeling is the force of the air and wind rushing past your car that go into the gap that is formed from the air moving quickly as the tractor trailer goes by. That is Bernoulli's principle at work. Well, I learned that in high school, and then literally that same day on the way home, I experienced it, and I was like, whoa, this is cool. But that's because of how fluids move. So, I mentioned about the speed of sound. Speed of sound is cool. So when you were talking, we talked about sound a bit a couple podcasts ago, way back. Sound travels through matter. Quick refresher. But it travels through matter at different speeds. And the speed of sound in a state of matter is dependent on the matter itself. It's unique for every piece of matter, or every type, I should say. And so air has a speed of sound of, I believe, 343 meters per second squared. Sorry, meters per second, not squared. It's a speed. And my mind thinks in SI. I know all you nerds out there can convert it to standard. But for some reason, like 636 is popping in my head, but I know that's not necessarily right. It's closer to 1,000, because there's 25.04 millimeters per inch, and there's 12 inches per foot, so 25.4 millimeters times 12 is your foot to millimeters, and then you divide by 1,000, and then you get your number, your conversion factor, and then you multiply that by 343, and then there you go. There's your speed of sound. But I think it's definitely over 1,000. These are numbers I had to memorize at one point, and I no longer use them, so I don't have to know. But that's the process of how you would figure it out. My great uncle used to always say, Daniel, you don't need to know everything. You just need to know where to find it. So, in this case, here's how you find it. You can also just Google it, but don't rely on Google forever. You never know when you're out in the woods and you're in a plane crash and you need to fly away again, repair the plane, and you need to calculate airspeeds and speed of sound. You never know. Never know. Anyway, so sound travels through stuff at a certain speed. But there's interesting properties around that. That's called going Mach 1, by the way. If something is traveling the speed of sound, it is going Mach 1. And that's named after, Mach is, another old physicist type guy. And so you have interesting properties when things travel at, around, or faster than Mach 1 and the speed of sound. And you get, there's different, we call them air regimes, or speed, volume, or velocity regimes. But there's assumptions that can be made for things traveling in between 0 and 0.3 Mach. Their Mach value, their Mach number, is between 0 and 0.3, is typically deemed incompressible flow, meaning, yes, gases can be compressed, but we're not feeling compressible effects here. Between 0.3 and 0.7 Mach number, you are getting compressible flow. And anything above that's going to be compressible, by the way. But that's when you start feeling subsonic compressible flow effects. And then from 0.7 to 1, you're still subsonic, but you're in this critical regime where going faster, up to Mach 1, requires a ton more energy to travel. And so, if you had the equation in front of you, it would make more sense. But it's dependent. The energy of traveling towards Mach 1, it's kind of like a dip. If you had it graphed out, or I guess it wouldn't be a dip; it'd be a spike, depending on what your axes are. But basically, to approach Mach 1, it's kind of like approaching the speed of light. Like, approaching speed of light requires near infinite amounts of energy if you have mass. But if you are approaching Mach 1, you also need a ton of energy to maintain Mach 1. And the reason for that is you get this thing called shock cones and Mach cones, which is friction effects of breaking the sound barrier. Breaking the sound barrier, by the way, and maintaining a break requires a ton of energy, because you get pressure effects, you get pressure differences. There's stuff that is flowing faster than the speed of sound, and then there's stuff you're running into that is not flowing faster than the speed of sound. And you get you've definitely seen a sonic boom, probably pictures of it, but you get these Mach cones off of things that travel that fast, and those generate sonic booms. But anyway, there's interesting. This is actually really not intuitive. It's not intuitive at all. But pressure, as you increase velocity, and let's assume temperature is the same. This is an adiabatic process, but as you increase velocity and you decrease volume, your pressure builds. It builds and builds and builds and builds until you hit Mach 1. It's kind of like if you ever take a garden hose and you put your thumb on the end of it, like the water is going to flow out faster because you've reduced the volume that the water can flow from, but the pressure in the back end is remaining the same, so the speed's adjusting. But if you adjust the speed, and you keep a constant volume, your pressure is going to drop. Now, if you raise the speed and you lower the volume, your pressure is going to increase. And this happens up until Mach 1.0. And then something very strange happens. And there's been much scientific discovery and research into this topic over the last 100 years. But when you go above Mach 1, this flips. It's very strange. To increase your pressure, you no longer decrease your volume, you increase your volume. Same with velocity. Basically everything that I described is flipped, is what happens. There's these things called converging diverging nozzles. If you're ever curious what this looks like, look up a converging diverging nozzle. Basically, just think of a tube and then pinch the center of it, with your fingers, so that it squishes in. That's what that looks like. And so what happens is you develop your converging diverging nozzle in such a way that air, when it flows through it, or whatever liquid you're using or fluid you're using, because this works with other fluids too, it's just harder with some things than others. But you energize in such a way such that it hits Mach 1 at the throat, at the choke point, at the smallest volume in that tube, or that nozzle. It hits Mach 1 there, right? It speeds up. It's speeding up as the volume is decreasing and the pressure. In this case, if you hold constant pressure and decreasing volume, your speed will increase. So it speeds up, in this case, as it goes to that throat. And then what happens is, as it opens back up, it's gone above Mach 1 now. To increase the velocity, you actually need to give it more volume. It's so inverted from your thinking. It's weird. It's like putting this little choke point in a tube makes your fluid travel so much faster on the outflow. And that is part of my aerospace knowledge. That is not necessarily practical for your day-to-day. But I sure hope that the viscosity conversation was, Bernoulli's principle, and just general gas laws would be. You can use this to... I didn't even talk about boiling points and freezing points a bit. I mean, I mentioned them, but that's a topic for another day. I think I covered that all in temperature and what it is. If I talked about temperature. I think I did. I talked about thermodynamics, and that covered temperature. Anyway, I just got home. I could talk about fluids for at least another 20 minutes, but I want to keep it practical, I want to keep it interesting, and I hope you enjoyed this mildly entertaining pep talk today on fluids and how they work. So, thanks for tuning in. Enjoy your Tuesday. I'm going to try and figure out what to do next. I'm very tired. But yeah, thanks for listening. Goodbye.